Hi everyone, in this video I'm going to show you the right way to model depreciation under straight line method. This method is extremely scalable and gives you accurate answers. Straight line method depreciation is one of the most messed up areas in financial modeling. Analysts often encounter a situation where their fixed asset balance goes negative because of excess depreciation, and then they end up using certain plugs to make the number look reasonable. More sophisticated modelers use what is called as a waterfall approach, which is considered to be a better approach, but I do not recommend that approach at all. In this video, I'll first tell you the waterfall approach, what it is and why it's a bad idea. After that, I'll show you the right approach. So the waterfall approach works something like this. So you create a waterfall section where you create separate row for each of the years that we have across columns. And in each of these rows, what we do is we calculate the annual depreciation of the capex incurred in that year and spread it over its useful life. So 2024 capex was 5,000. It's spread across its useful life from 24 to 27. And similarly, 25's capex is spread between 25 to 28 and so on. And depreciation amount is simply going to be the column total of the waterfall section. Why is it that I don't recommend this? Because in this case, what's going to happen is if we were to extend our model by one more year, let's say 2030, I'm copy pasting, but we are not done yet. We have to do many manual steps now. So I will have to copy this row in my waterfall section, add it. That's one manual step. Change the capex here to 2030 so that my model picks up the 2030 number. That's two. And the depreciation cell, right? Earlier it was totaling from 24 to 29 because 2030 did not exist in my waterfall section. I will have to change that formula as well. That's three manual steps. This is okay if you're trying to build a calculator, but if your idea is to build a model, this is a bad idea because models need to help us in simulations and that needs to be extremely automated. So let's see what's the right approach. So here is the approach that I recommend. What we're going to do here is that instead of creating a separate waterfall section, we are simply going to add a single field here, which is going to calculate the annual depreciation of the capex. In this case, we are assuming that there is no salvage value, which means the annual depreciation under straight line method will simply be capex upon the useful life of the asset. Let's copy and paste it for all future years. Now, if you think about it, the depreciation for 2030 will be the depreciation of all the assets purchased in the last 4 years because that's the life of the asset. So what I'm going to do is use a simple sum function, sum of depreciation of assets bought in the last 4 years. This is not the final solution, but let's understand this. I'll copy and paste it to the start of the year, and you could see here the answers are precisely same as what we got with the waterfall approach, but we were able to get this without the waterfall section having to be created. There is a bit of a problem here though. That's why I said sum is not the final approach. This is simple, pretty easy, but this is not dynamic. So if the life of asset becomes 5 years, what we notice is that while the annual depreciation is reduced, my summation is not expanding to 5 years. I'm still summing up only the last 4 years. To tackle this problem, I recommend using SUMIFS function. So what I'm going to do is I'm going to use equal SUMIFS, select the depreciation section. This is what we have to depreciate. And the criteria here is going to be in the year section. Keep in mind if the life of asset is 5 years, then in 2030, I'll be depreciating everything bought in the last 5 years. And that's going to be everything bought after 2025. 2030 minus 5 is 2025. And everything bought after that is going to be depreciated. So the condition is going to be that the year should be greater than current year minus the life of the asset. So current year is 2030 minus life of asset. And that is going to give us the answer here. If you're using relative referencing and the traditional architecture, in that case, I would recommend that you freeze the starting row, but do not freeze the ending part. In the sense, do not use a dollar sign for the ending part of the range so that when you copy paste, the ending section can keep increasing while the starting remains fixed. So let me copy and paste this. And again, we would see that we are getting exactly same answer as what the waterfall approach gives us, but without the need to set up the waterfall section. What is the advantage? I can easily copy paste this and you would see that this is giving me correct answer. It takes into consideration all the past capex, unlike the waterfall structure, because in a waterfall structure, as we saw earlier, we had to copy paste more rows as well. That was a limitation, which this one takes care of. We can also use this approach to model a more dynamic situation, which I have in the next sheet, where we are talking about a situation where the life of asset is not static. In the previous example, we took the life to be static, where we assumed all the capex are 5 years. In this case, we're going to talk about what if the life of asset were different for different year capex. Not a big problem at all. What I'm going to do is just like what we did earlier, let's calculate annual depreciation for capex. And that is going to be equal to current year capex divided by the life of asset. Again, assuming no salvage value. We'll copy and paste this. I'm going to add one more helper row here, which is going to be retirement year for the asset. If the asset is being bought in 2024, we are assuming it's bought at the beginning and has a life of 5 years. So the retirement year is going to be 2024 plus 5 minus 1. That's 2028. So we will be depreciating it from 2024 to 2028. So let's calculate this for all the years capex. And all I'm going to do is this. Sum up the depreciation as long as the asset's retirement life is in the future or in the current year. So this is simply going to be sum ifs the depreciation, annual depreciation that we calculated, where the retirement year is in the current year or in the future. So retirement year is greater than or equal to current year. Again, let me fix the starting column here. We don't want to fix the ending column, but I'll fix the starting column. Copy and paste. And we have the answers working. Again, whatever the waterfall approach gave us as the answer, we can see here, we are getting exactly same answer. And this is a far more scalable approach. What is in application here in terms of mathematics? Excel, it's sum ifs, but in mathematics, what we are applying is simple set language. We are just trying to figure out what is the data that should fall in a given year, right? And when you develop the set language thinking, we can even make the models far more scalable, like what I have here. So in this case, I have lots and lots of assets with different start date, even salvage values, different life, and bought on different dates. Some of the assets are bought in the same year, but with different life and different salvage value, and we would still be able to crunch them all in a single schedule like this. And in fact, I have here developed a lambda, which is going to give me the entire answer with just one single formula. So I'm going to go to FA schedule, the original cost, the salvage value, the date of purchase, the life of the asset in months, the first year for my model, let's say that's going to be 2024. And let's say I need the model for 7 years from there on, and I want all of the answers in thousands. One formula gives me the entire schedule. And the thinking process behind that is exactly what we just discussed earlier. That's a good building block. So to be able to build a scalable, highly powerful lambda like this, what you need is the right thinking process, the mathematical thinking process, as I would say, rather than thinking about how do I lay it out in a spreadsheet. If you can crunch the problem and reduce the problem using mathematics, you can build extremely scalable schedules. I hope you found the video useful. See you next time. Thank you. Bye-bye.